Hi everyone, today's lesson is lesson 1.1 and we're going to be covering significant figures and scientific notation. Significant figures will likely be a new concept for most of you. If you happen to be in physics right now, you're probably talking about it in that class as well. So some grade 10 teachers do it as well, but most of you will probably, this will be your first exposure to it. Scientific notation, again, this you've probably seen, you've probably had some experience with, but we're just going to quickly review it and just make sure that it's all pretty solid there and you know what you're doing. Okay, so first of all, we're going to start with our sig figs here. So what are sig figs? So first of all, significant figures, we're going to abbreviate that sig figs. So in science, all numbers are based upon measurements, except for a few things that are defined, and those would be considered constants for us. Since all measurements are uncertain, there's no perfect measurement, we must only use those numbers that are meaningful. For example, we've got a common ruler here. If you were to measure something, you wouldn't be able to get a whole lot of detail out of that. So for example, using that ruler there, I would not be able to measure 22.4072643 centimeters exactly. You know, I could probably get it close to, I'd get 22.4. I'd be able to do that, but I wouldn't be able to get all those digits here, these little ones here. So not all of the digits have meaning in that number. They're not significant, and therefore they shouldn't be written down in this case. We would just write the 22.4, and we would estimate one more. So this would actually round. This number, using this particular ruler, would be 22.41. However, if we were to use something like a vernier caliper, which is this device here, this allows us to get more significant figures. So it allows us to measure something to a greater detail. And we're not going to use the vernier caliper. I'm just showing you that as an example. You may have used that in your grade 10 course. But anyways, so depending on what instrument you use, that's going to determine the significant figures that you have. So we're going to go through the rules for significant figures, so how this stuff is playing out. So number one, first rule, and you want to be writing this down in your notes, okay? So just pause the video as you need to be able to write stuff down. So all non-zero numbers are significant, meaning they count as sig figs. So these numbers are, I'm going to know for sure that they are significant. So for example, the first one, 613, those are all non-zero numbers, so we would say that this has 3 sig figs. Now the next number, which is 123,456, or 1, 2, 3, 4, 5, 6 here, this is going to have, again, they're all non-zero, so they all count, so this would be 6 sig figs here. Now, second rule, zeros located between non-zero digits are significant. They count. So even though they're zeros, because they're in between two non-zero numbers, we're going to count them. So the first one here, 5,004, 4 digits long total. There's 2 zeros, but because they're in the middle there, that's going to count as 4 sig figs. 602, again, that zero's in the middle, so that's going to have 3 sig figs. And then this number here, we have a whole bunch of zeros here, so I'm just going to count them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is actually going to have 10 sig figs for this one. And those zeros count again because they're in between two non-zero numbers. Trailing zeros. So the third rule talks about trailing zeros. So zeros that are trailing are those at the end of a number. They are significant only if the number contains a decimal point. Otherwise, we don't count them. So for the first one here, 5.640, that 0 at the end does get counted because this number has a decimal in it. So I'm going to count 4 sig figs for this number. The next number here, I've got 1,200,000. Now I've got a decimal there, and that decimal is showing me that all of those values are significant. So what that means is you've got 1,200,000 exactly. So it's exactly that to the ones, like you know that for sure. So this is going to have 7 sig figs. Sorry, that 7 looks a little funny. There we go. Whereas the case right underneath there, the 1,200,000, this one does not have a decimal at the back of it there at the end. So what that means is that I only know this number for sure to that 2 value. Everything else would be considered insignificant or we don't know for sure. So there's got uncertainty. There's uncertainty in that number. So that tells me that that number could be 1,232,000, for example. We don't know. I only know for sure up until that 2, up to the 100,000 place value. So for this one, we only have 2 sig figs for that one. So there's a big difference, for example, between these two numbers then, between the one with 7 sig figs versus 2 sig figs. The one with 7, that is an exact number. The one with 2 is like an estimate. So there's a lot of uncertainty in that one. We don't know that number for sure. Number 4, zeros to the left of the first non-zero number or digit are insignificant as they are only placeholders. So we don't count them as significance. They're just showing us where the placeholder is for the value of the numbers. So for example, the first one here, I've got 3 zeros in front of that 4, 5, 6. Those are just placeholders, so I don't count them. So this one has 3 sig figs. The next one, I don't count that 1 0, it's got 2. This one here, again, same thing, only 2 sig figs. Even though there are all those zeros in a row here, they don't count as being significant, they are only placeholders. And the next one, this one's a little different. So now, this 0 doesn't count because it's a placeholder. However, these 2 zeros are trailing zeros, so those ones will count because of that decimal. So this one here has 4 sig figs in it. Now, we have rules specifically for when we're adding, subtracting numbers, and multiplying and dividing. And you are going to use this in a chemistry class. And so because all chemistry questions, I mean, we do them on paper, but they came from real life or they came from being in a lab. So they're all based on measurements that had been taken at some point. So we need to know these rules, and we're going to use them throughout the entire course, okay? Now, so when we're adding and subtracting, your calculated value cannot be more precise than your least precise quantity used in the calculation. It's kind of a lot of words there to make sense of, but what that means is your answer cannot be more precise than the initial numbers that you had. So the initial data that you have, that is going to determine what your final answer is going to be. So for example, here we have 7.939 plus 6.26 plus 11.1. So if you put that into your calculator is going to spit out 25.299. So this is showing me 25.299. If I left the number as this would mean that I am sure all the way up to, remember we've got the tenths, the hundredths, and the thousandths, that I'm sure up to the thousandths place value. But not actually true. If I look back at my numbers here, let's look at this 7.939. Yes, that one I know to the thousandths, so that one is very precise. But the 6.26, I only know that one to the hundredths. So I don't know what the thousandths value is for that one. And then the 11.1, I only know that to the tenths. So because I only know that one to the tenths, that is my least precise value. So that means my answer cannot be more precise than the tenths. So I have to round my answer to the tenths place value. So my answer is going to be 25 and I'm going to round it, so 25.3. So now I've written it properly. That is to the place value that I know. Now there is different notation. So some people, and you can feel free to do this, you can keep the number whole and just use a bar over top to indicate where the significance is. figs. And significance is going to be right there, right? So again, over the 10ths place value. Both of these answers are correct. You can choose which one you want to do. So you can round, like in the first case here, or you can just use a bar over top, your choice. Now, rules for multiplication and division. These are a little easier. So the number of sig figs in the final calculated value will be the same as that of the quantity with the fewest number of sig figs used in the calculation. So basically, what you have to do is look at the numbers that you were given first and find the one with the smallest number of sig figs, and that's what your answer is going to have. So let's look here. This one, 27.2, has how many sig figs? 3. 15.63 has how many sig figs? 4. 1.846 has 4 sig figs. Now I'm going to pick the lowest number of those. So your answer cannot have more than 3 significant figures. So let's look here. I've got 230.3011918. So I have to round it. I can either put a bar over top like that, or I can write 230. But if I wrote 230 just like that, how many sig figs is that actually showing? Yeah, it's only showing 2 because this 0 does not count unless I put a decimal there. Now, usually people don't like doing this because it looks weird, it feels weird to them, but it's fine to do that. So 230 decimal would be how you would write it, or you could use the bar over top. Now, rules for combined operations. So this would just be when you put things together, and you're just going to follow, hold on here, you're just going to follow your BEDMAS for this. So I'm just going to write a question here. So 3.42 plus, oops. Okay, so if you're going to type this into your calculator here, so I'm going to do the brackets first, right? So 3.42 plus 1.8 equals, and I'm going to multiply it by 9.431. And I get an answer of 49.22982. Now, right away I should say, okay, that is not the correct significant number of significant figures. So I need to look at the question to figure that out. Gonna use a different color here. Okay, so first one. Now, the first part here in the bracket, this is addition. So because it's addition, I have to look at place value. This one is the 3.42 is significant to the 100ths, but the 1.8 is only significant to the 10ths. So my answer here between these two can only be significant to the 10ths. So I'm going to do that. So 3.42 plus 1.8 is 5.22, right? So 5.22. But from that, I know it's only significant to there. And then I'm going to multiply it by the 431. Now I look at the sig figs though. This one has 4. This one only has 2 sig figs. So my answer can only have 2 sig figs. So you're going to put a bar over top there. That is going to be your answer. So, or you can round it then just to 49, and 49 will be your answer. So you have to maintain and follow all the rules when you're using combined operations. Okay, we're going to move on to scientific notation here. So we use scientific notation to write large or small numbers easily. So for example, we have 6,400,000. It's kind of a pain if we have to write that out all the time. So generally, or say it even, so generally speaking, we're just going to use scientific notation to make it easier. And we use this in science a lot because a lot of the values we deal with are very large or very small. And in chemistry, you know, we deal with very small particles. So in order for us to see any big changes in atoms, for example, we need a lot of atoms so that we can see changes. Just a second here. Okay, so we're just going to go through some examples. I think most of you will have seen this before. For example, let's say we have 3,421,000. And I asked you to write that into scientific notation. So what you're going to do, you're going to imagine where the decimal is. The decimal's here. So you're going to move it over. So you're going to go 1, 2, 3, 4, 5, 6. So I moved that 6 spots. So in scientific notation, it will be 3.421, and then I don't write the 3 zeros, times 10 to the 6th. So that is the answer in the number in scientific notation. Oops. Okay, if I had 6,100 or 6,100, and I wanted you to write that in scientific notation. Again, I'm going to put the decimal here, move it over, 1, 2, 3. Typically, with scientific notation, you just have one digit followed by the decimal, so you move the decimal over till you only have one left. And so this is going to be 6.1 times 10 to the 3rd, because I moved it over 3 spots. So this is how these work that way. So try this one on your own. Oops. Hold on. There we go. So 72,000. So try that one on your own. Just pause the video and do it. Okay, so you imagine the decimal here, move it over 1, 2, 3, 4 times. So 7.2 times 10 to the 4th ends up being your answer in scientific notation. Now, these are all for very large numbers, but we can use them for very small numbers as well. So, as an example, we've got 0.00034. If I were to write that in scientific notation, I'm going to move that over 1, 2, 3, 4 times. So this is going to be 3.4 times 10 to the negative 4. And so we change the exponent here is now a negative. So if I'm moving the decimal over to the right, I'm moving it, so I have a very small number and I'm moving the decimal over, the exponent has to be negative. So again, 0.000, let's put a bunch in here, 639. So looking at this, I'm just going to move that decimal over. So I moved over 1, 2, 3, 4, 5, 6, 7. And my answer then 6.39 times 10 to the negative 7. Okay, so that's scientific notation. You can just refresh your memory of that, do some questions on that, and then make sure you ask me any questions in class if you have some. So now exercise 1 and exercise 3 are assigned. Exercise 2 was naming, but you should have done that in your review, so hopefully you're all done for that. So we're going to correct these assignments next class, so be sure to have the assignment completed by then. Okay, that's it for today. Thanks, guys.